Hi, my FYP topic is TFIDF meets Deep Document Representations, a revisit of code training for text classification. I would like to express my sincere gratitude towards Professor Sun Aixin for guiding and supporting me throughout this journey. As of today, both TFIDF and word embedding-based representations are sufficient to represent a document, and they are from different feature spaces. This motivates us to revisit code training algorithm to explore whether the two sets of document representations can facilitate us to utilize unlabeled documents in text classification. Thus, we conduct experiments on two benchmark datasets, namely 20 newsgroup and OwnZooMed, using 5 different document representations: TFIDF, Doc2Vec, which is based on pre-trained word-to-vec embeddings, and 3 other deep contextualized representations, the Elmo, BERT, and Universal Sentence Encoder. This is the agenda for this presentation. In real life, we often face the situation of inadequate labeled data to learn accurate text classification models. It is often very expensive to obtain more labeled data. Among many possible solutions, the code training algorithm is a solution designed to utilize both labeled and unlabeled data. Code training assumes that each instance is described by 2 views. The 2 views are expected to be conditionally independent, and each view is sufficient to predict an instance class label. With a small number of labeled examples, 2 weak classifiers are first trained, where each is trained with 1 view. Both weak classifiers are used to predict the labels of unlabeled instances, and the instances with most confident predictions are added as labeled instances to learn better classifiers. The code training algorithm shows effectiveness in web page classification, where a web page can be described by its content and also the anchor words pointing to the web page. We have made slight changes to the original code training algorithm, and here it is. Now I will talk about the experiments and the results in detail. These are the metadata of 20 newsgroup and OwnZooMed. To evaluate code training, we randomly sample 10% of labeled documents from each class to form the label set L. The remaining 90% of training data becomes U. We set the size of U prime to be 400. After each iteration, the top P most confident documents from U prime are added to L. We set P equals to 1 for the first 10 iterations and increase the value of P by 1 after every 10 iterations. After k equals to 40 iterations, we have in total 100 documents added to L. Then we stop code training and evaluate the combined predictions of the 2 weak classifiers. Also, in order to provide reference performance for code training, we first evaluate the different classifiers normally trained on different document representations using labeled documents in L, which is only 10% of the training data, and documents in L plus U, which is 100% of the training data. We report the classification performance by macro average, precision, recall, and F1, as well as accuracy. In our discussion, we mainly focus on F1 score. The first 2 columns are results for 20 newsgroup, and the last 2 columns are results for OwnZooMed. Performances on both datasets shares similar trend. All classifiers show significant drop of performance when only 10% of labeled data are used for training, compared to the version using 100% training documents. Overall, OwnZooMed is much more challenging to get high classification results. The best performing model for each document representation are highlighted by the boxes. Our results suggest that deep contextualized representations, together with the right choice of classification models, are likely to achieve the best results. Nonetheless, TFIDF plus SVM remains as a strong baseline. As some of the models give very poor results, we only choose the best performing classification model for each of the 5 document representations, that is, those that are already highlighted by the boxes. Then we will conduct code training on this set of classifiers. With 5 document representations, we will have 10 combinations of H1 and H2 for code training for each dataset. The upper region reports on 20 newsgroup, the lower region reports on OwnZooMed. After code training, we report macro average, precision, recall, F1, and accuracy of the combined classifier H3. We mainly focus on F1 score. For comparison, we compute delta F1L, which is the change of F1 obtained by H3 compared to the lower bound. The lower bound is determined by the F1L of the better classifiers among H1 and H2 when trained with only 10% of training data. It can be found in the previous table. Accordingly, delta F1 denotes the difference between H3's F1 score and the upper bound, which is the F1 score of the better classifier among H1 and H2 trained with 100% training data. We also list the error rate of H1 and H2, which is the rate of wrong predictions made by weak classifiers when adding documents to the training set L. Those highlighted in boxes are those with positive delta F1L. From the results, we make the following observations. On 20 newsgroup, 5 classifier combinations in code training setting has significant improvement in F1 score. Comparing these F1 scores to the F1 score of a single classifier obtained by using all labeled documents, the improvement is promising. We also note that the error rate is fairly low for both H1 and H2 on 20 newsgroup. On OwnZooMed, only one combination managed to get a positive delta F1L, and the improvement is not statistically significant by paired t-test with 2 tails. In other words, code training results on these datasets are in general worse than the weak classifier H1 and H2 when training with limited labeled data. We also note that the error rate of H1 and H2 for OwnZooMed is fairly high. In summary, the evaluated co-training combinations show very different results on the two datasets. On a typical classification task like 20 news group, we observed improvements on 5 out of 10 combinations of classifiers after co-training. The classification models in each combination leading to improvement could be the same or could be different. However, in all the 5 combinations leading to improvement, the weak classifiers at H1 and H2 are both among the better ones compared to the other classifiers. On a challenging classification task like ONSILMAT, we do not observe the benefit of co-training, probably due to the weak performance of weak classifiers H1 and H2. With relatively high error rate, the quality of documents added to L is not ensured, leading to the classifiers in the following iterations to learn from noisy labeled data. We have come to the end of this presentation. Thank you for your attention.